Okay. Hey, hello everyone. So we're gonna start the presentation on our reading group. Just make sure the recording. I'll just make sure the recording is starting. All right, it's going on. Okay, so we're gonna start right away with a little summary of what's been seen over the past weeks. I don't know. We've seen groups and subgroups, and we've seen a lot also on group homomorphism, which is a map from a group to another one that preserves the group law, that is for any AB, f of AB equals f of A times f of B. And we saw that each group homomorphism gave rise to important subgroups, namely the kernel of f, which is a subgroup of the original group, the set of all elements that's mapped to 0, so such that f of x to the identity element of h, and the image of f, which is just the set of all elements from mapped from G. So that is kind of, that's why it's called image. It's kind of a transportation of G to the new group, so that G kind of lives in the new group. And we've seen that those are both subgroups. Some additional important properties of groups I've seen someone mention in the exercises section is that if you have a subgroup, say S, a subgroup of G, so we're just going to recall that a subgroup is a subset that is stable under the multiplication of the group, and also has the identity element. So if S is a subgroup of G, it also gets transported by the morphism to the group H. So f of S is a subgroup of G, of H, of f of G, which is the image of f. So a few examples of this are, for example, if we have a morphism from the set of permutations of order n to the set of matrices by using the permutation matrices. Permutation matrices are, so for example, take S3. We can write each permutation as a matrix. So for example, the permutation that sends 1 to 2, 2 to 3, and 3 to 1 can be written as a matrix by indexing the columns as the original set. So this will index the columns, and for each column the number that it gets mapped to is the index of the line in which we're going to place 1. So for example, 1 is sent to 2, we're going to put 1 here. 2 is sent to 3, we're going to put 1 here, and 3 to 1, we're going to send 1 here, and 0 everywhere else. And this is called a permutation matrix. And the map that sends each permutation to this matrix, which we're going to call P sigma, is a group homomorphism from Sn to G, and then the set of invertible matrices again. We can check that this is actually indeed invertible, the resulting matrix in this operation, because for example the 3 column vectors are never both equal to 0 if you multiply them by some scalars and add them up. Or just check that if you take any square region 2 by 2, you can find 1 somewhere. So it's never all 0, no matter how you permute the columns and lines. You never get a 0 column or line. Okay, so that was an example of a morphism. The kernel of this, so the kernel of this F is sigma, such that its image is the identity matrix. So what would that be? If we had a permutation that gets sent to this, we can just translate the identity matrix back to a permutation. So an example in S3 again. By how we constructed this matrix, each coordinate ig is 1 if in the permutation I gets sent to j. So since 1 1, this matrix coefficient is 1, this is coordinate 1 1, it means that in a sigma 1 gets sent to 1. This being 1 means that 2 gets sent to 2, and this means 3 gets sent to 3. So sigma equals the identity on 1 to 3. And so the kernel of this morphism that we presented here is only the identity element. This little computation means that if any permutation satisfies that it's in the kernel, it must be the identity element, so that the kernel consists of only one element. And not sure if this has been seen already, but if you have a group homomorphism from G to H, F is injective if and only if its kernel is the identity element of G. So in this case, we see that the kernel of this particular morphism is the identity. So F is injective. Injective means each element of G has one image, and that image is the image of no other element in the same group. It's a very important case when you see an injective morphism, homomorphism, because if this is G, for example, this is H, and say you had 1, 2, 3, 4, 5, 6, 7 elements, and H has many elements. If G was not injective, if G was not injective, if the morphism was not injective, some elements would have the same image, for example, as so. And the image of G, while being a subgroup, will not say much about the group itself. Not that homomorphisms are only important when they're injective, but when they're injective, say a group with 3 elements with a homomorphism to a group with 7 elements. If we had an injective morphism like so, the image of G in H, which is these 3, look like an exact copy of the original group, so which is a subgroup of H. So actually, when the homomorphism is injective, it creates an isomorphism from G to the image of the morphism. So recap, if F is an injective homomorphism, G is isomorphic to a subgroup of H, and that subgroup is F of G, or the image of F. So what this means, for example, if we're back to the previous example of permutation matrices, it means that the set of all matrices with one coefficient equal to 1 on each column and 0 everywhere else, such that each line has exactly one value equal to 1, is isomorphic. Well, the set of all matrices is isomorphic to the permutation group of order n. And so we can deduce a lot from an isomorphism. For example, the order. It means that there is the order of this matrix subgroup is equal to the order of Sn. So let's write it clearer. Let's note Pn, the set of permutation matrices, that is the matrices satisfying that there's exactly one non-zero value on each line and on each column is isomorphic to Sn, so has the same order. It also means that, for example, since Sn is not abelian, the permutations do not commute, the set of permutation matrices also do not commute, because a few properties are preserved by isomorphism. So that's, I think we've seen that as well. Other properties, if F is an isomorphism, not just any morphism, by the way. So isomorphism is when it's bijective on top of being a group homomorphism. The following properties are preserved. If G is abelian, then so is H. Yeah, if G has subgroups, well, other than G and 1, so does H. And then there are other properties that I don't think we're gonna look at yet, but, well, the second property can sound a bit obvious, but some groups may not have like subgroups H that is strictly inside G. So if this is G, in some cases it's impossible to find, well, it's with certain properties it's possible to find a strictly contained H, but that's not too important. That's pretty much all about the summary of what we've seen so far, and a bit more on isomorphisms. If, by the way, the co-presenters, I have two co-presenters, one co-presenter. If you have anything, do not hesitate to ever interrupt me at any time at all. Alright, so we're gonna continue with subgroups H. Yeah, a new property on subgroups.
Real quick before we move on, a question from the chat. If a subgroup is only the identity, would that be an instance when it doesn't have a subgroup? Is that the sort of thing you're talking about?
Yeah, for example, if a group is only the identity, does it not have a subgroup? Yeah, for example, that's an example, I guess. If G is only one element, is that, wait, am I understanding the question? Is this is a group that does not have a proper subgroups, because any subgroup of this must contain the identity, and so it must be the whole. Okay, if H is a subgroup of G, by definition the identity element must be contained in H. So since there's only that element in G, it means that the whole of G is contained in H, and so G is H itself. Actually, I'm not sure. I thought there would be some groups that do not have strict subgroups at all, but actually I don't know where I heard that. I thought about normal subgroups, which is not the case. Yeah. But yeah, that's the very next thing I'm gonna present is normal subgroups. So,
Sorry, the question is clarified.
okay.
So it says if G has subgroups, then so does H, right? This is from the
Oh,
isomorphism statement earlier.
correct.
So we're trying to square that statement with this subgroup being the identity business.
Okay, so in this case, right, if the subgroup of G is the identity, is that the question? Oh, okay. I think.
Kirby, is that the question? One thing. Sorry.
He basically said, where'd the screen share go?
Sorry.
But anyways, he basically said that if G has subgroups, then so does H. But if we define H to be the subgroup only containing the identity, then that wouldn't have any subgroups. So wouldn't that be a counterexample?
Okay, wait. Let me just set up the stream again. Okay, so wait. Sorry.
You're good. We're seeing it though.
All right. So the counterexample was if H was the identity group. Wait. Note that this is isomorphism. So if we have an isomorphism from G to H, right? Do I understand clearly that if H was just this, is this what's been asked?
Yeah, because that wouldn't really have any subgroups.
Yeah, but if this was H and this was isomorphism, since this means it's bijective, it means G is also just the identity. So
I see.
the isomorphisms means that they are exactly the same. But actually the reason that's a really good question, but it's because how do we know that there exists a subgroup of G of H? So the proof goes as follows. If we found, for example, a subgroup H of G, no,
perhaps K, yeah.
names. If we have a subgroup K in G, if we want to find a subgroup of F of G, the main candidate is F of K. Right. So it's just F of K is a subgroup of F of G. So if we have our original G going to H, say this bigger one is H and this is the copy of G inside H, whenever we have a subgroup in G, that also gets transferred with the isomorphism into its copy. So it's kind of like a mirror in some sense, in some way, that copies everything, whatever is in G, to its image, so that they look exactly the same in terms of the group law and everything. Since the group law gets preserved, it works. But yeah, is that did that answer the question? I think.
Yeah, I think so.
Okay.
Thank you.
You're welcome. Do not hesitate if anyone else ever. And thank you for mentioning the chat, because I'm not at all looking at the chat at all times.
Yeah, for sure. I can keep monitoring that for you.
Yeah, thanks. Alright, so we're gonna introduce a new property that subgroups may have. Property of subgroups, which is normality. So it just a definition. Let if H is a subgroup of G, H is normal in G if for any G and any H in the subgroup, when we multiply H by G on the left and by the inverse of G on the right, it stays in the subgroup. So it looks like a very weird, complex, useless operation, but this is called the conjugation by G. And a subgroup being normal is very important to understand the structure of a group. For example, in the group of matrices, always in a group of invertible matrices, say we had some subgroups, some subgroups H, well, so some set of matrices H in the group. If H was normal and we had a matrix M in H, if we took any matrix P M P minus 1 would still remain in H. And especially for those who have seen some linear algebra, for example, if P is a change of basis matrix, it means that if this is a change of basis operation, which happens in linear algebra. If we change the basis, the subgroup is stable under that operation. Or in more clear way, I think, well, not more clear, but if we took the permutation group S3, what would it mean for something if we had two permutations, tau and sigma? What would it mean for this to be resulting in another permutation? So say we have the set 1 to n, because that's what permutations is, going to 1 to n. The operation on the left is taking an element, its image through sigma minus 1, then taking its well, I chose the wrong format again, I think. Okay, if we had elements from 1 to n, take its image with sigma minus 1, take its image through tau, and then take its image through sigma again. Well, somewhere. Yeah, I chose wrong format to display this. Uh, but the point is that it's very unlikely that you'll end up with the same number if you composed, for example, if you took of 3 and f of 3. It's unlikely, well, intuitively for me, it's unlikely to end up with the same result. And even if we do not restrict the criteria to be the same result, if, for example, if we characterize permutations with certain values, like the signature, so the signature morphism. Might have seen this example in the book quite often. The signature assigns to a permutation. So say we had 2, 4, 3. This, we can count the amount of times that integers are swapped places from left to right. For example, in this case, 1 sent to 1 and 4 sent to... Wait, I'm not sure how to construct this. Yeah, okay. So, is anyone speaking? Okay. 1 gets set here, and 4 here. Wait, I think this is the permutation. If someone has the information, let me know. Is it sigma I, sigma j? Okay.
Sorry, I'm a bit lost.
Yeah.
What is this? What is this epsilon?
The signature. I'm trying to introduce the signature morphism. The sign. Wait. Signature. How? Wait. From Sn to plus or minus 1. Is this a standard notation? Wait. Not sure. Okay. Sorry. I'm gonna redefine everything. Not everything, but let's construct.
Maybe quick before you do that. I say quick. This might not be quick.
Okay.
The question in the chat is are normal subgroups necessarily abelian? And maybe just sort of more generally, can you comment on the relationship between normality and commutativity?
Normality. Okay. Normal and commutativity. Not sure I saw this property actually. If H is normal in G, so let's suppose H is normal in G. It does not necessarily mean first that G is abelian. That's actually if G is abelian, for example, let's take any random subgroup, any arbitrary subgroup H, subgroup in G, and let's do the normality check. So we take any G, we take any H, is G H G minus 1 in H. If G is abelian, this is equal to this, since you can swap places however we want to, and so this is just equal to H. So it is in H. So in an abelian group, this is a general property, in an abelian group, any subgroup is normal. So for example, if we want to check this property more in a concrete way, if we took the additive group of integers and took a subgroup, we've seen that subgroups of the additive integer group is subgroups of this type. So this is, so for example, say the even numbers, let's say the subgroup 2z, even integers. If we take any integer and did this check of normality, translate it into additive operation, this gets written as p plus 2k. So this is the element of our subgroup, plus minus p. This is just g h g minus 1 in terms of addition. The abelianness, this is, we can calculate this by cancelling the p out, so it's 2k, and it remains even. And this works for any abelian group or subgroup. So that's one relationship between abelian groups and normal subgroups. Now about the subgroup itself that is normal, do elements in H commute? Is that, I think that's the question, if H is normal in G, and if we took H1, H2 in H, is H1, H2 the same as H2, H1? No, it is not. And a counterexample is given by the alternating group. I think, or more matrix. Whenever we want to see counterexamples on non-commutative groups and its properties, it's very standard to check the matrix groups. So let's take, for example, matrices of determinant 1. Wait, before I can introduce this, there's a property of morphisms that the kernel of any f is normal if f is a morphism from G to H. Its kernel is normal. This follows from the fact that if, say, x is in the kernel, it means f of x 1g wait, why is it normal? Not sure. F g minus 1 is f of g times f of x times f of g minus 1 for any g. So the normality check is to check if g minus 1 is in the kernel, and this follows from the group homomorphism property, and this is equal to 1 because we suppose that X is here, so this equals to FG, which in two ways we can show that this is equal to 1. So first way is to see that this f of g is the inverse of fg minus 1, or we can also be really go back using the morphism property and see that this is f of 1g, so that is equal to the element of h. So the important thing is that if you have any morphism, its kernel is a normal subgroup. It's an easy way, not easy, it's a way to decide whether a subgroup is normal, for example. For example, if we took the group of matrices that are invertible, and I take the subgroup of m's such that they have determinant equal to 1, it is a normal subgroup because of the previous property, using a certain morphism which is the determinant. What this means is, more concretely and less abstractly, is that if you have a matrix M that has determinant 1, the determinant of this is also 1. And you may have seen that already in matrix computing courses, readings. And the proof in a matrix environment is exactly using that the determinant of p minus 1 equals that it preserves the multiplication law. So it's using that it's a group homomorphism. But this is an example of, since this subgroup, also called the special linear group, or SLN, is the kernel of a certain morphism, which is the determinant, is normal but unless I'm horribly wrong, it is not an abelian subgroup. Counterexamples of matrix with determinant 1 that do not commute, well, I don't know, let's check. Let's check, for example, do these commit? Not sure. So this is gonna give us 2, 1, 1, 0. The other way around would give us 1. Okay, so it's not, they don't commute. It's already not the same with the first coefficient. So this times this is not equal to the other way around. So H normal does not mean that H is abelian. Okay. However, there is a normal subgroup in G. So notice that why this does not work is in some way because we do not require GH G minus 1 to be equal to H we do not require them to be exactly the same. We require it only to be any other element in the original subgroup. If we required that H0, G minus 1 is equal to exactly H0, this would mean that GH0 equals H0G, and that H0 would commute with any element of the group. And this is actually a subgroup, an important subgroup of any group, which is called the center of G, which is the set of elements, I'm going to call them Z, in the group, such that for any G, such that any other element commutes with them. So this is the center of G, and this is a normal subgroup of any group. This is equivalent to saying that Z equals G. So note the difference between normal and center of group. A group, if an element in the center means it commutes with any other element. If G was in just any random normal subgroups, it does not mean this property. So the center can be hard to compute. For example, the center of, since we know that GL, the group of invertible matrices, is not commutative, if we found a matrix in the center of this group, it would mean that any other matrix would commute with them. So that's not easy to find, I think. But for example, the identity element of any group must be in the center, since it commutes with any other element. So this matrix will commute, well, zeros everywhere apart from the diagonal, commutes with everything else, so is in the center. Matrices with diagonal elements, all the same, also commutes. So these are some random real number, t, say t. Why is that? Two ways to show. Either directly, we can show that if we took any matrices, Mij, well, if we multiply this matrix with a matrix M, we can rewrite this as T times the identity. And the identity is equal to M. Well, the identity times M is equal to M, so this is T times M. This is scalar multiplication, by the way. So, for example, T times 3, 4 is 3T, 4T, etc. So, yeah, if we now multiplied M by M minus 1, this would give us D M minus 1. And since scalar multiplication can be swapped, kind of. For example, 3 times you can take this 2 here and place it at the beginning. It won't change. You can do the same for this, so it will give you t times the identity. So that is t. So the take is that matrices with all equal diagonal elements and 0 everywhere else, the subgroup formed by such matrices commutes with any other matrices, so it is in the center of the group. Other examples of center properties, more so, if G is abelian, again, this time let's take any element G. Let's do the center check, kind of. If we took any H times G equals G times H by the abelian, its immediate definition. So any G is in the center of the group. So the center of an abelian group G is the whole group. And the center of any groups, I think I've mentioned this, is normal. Is normal in the group and is contained in any normal. Wait, not sure. G minus 1. Nope, nothing. Okay, that's all about groups, the definitions. So if there's any questions, they're welcome, because I'm gonna start a new thing, or if co-presenters want to add stuff, fine. Okay. So automorphisms, I don't think. No, it's relevant. Okay. Briefly, a type of isomorphism that is important are isomorphisms from a group to itself. If F is an isomorphism, it is a bijection that also satisfies the homomorphism property. So a bijection that f a b equals f of a f of b. So quickly, examples of automorphisms for general, for any group G. If we fixed an element alpha, we define a map from G to G that is simply the multiplication by alpha, and F is an automorphism because we can check do the morphism check, the homomorphism check, which is quite immediate. And as for it being a bijection, we can see that if two elements have the same image, by cancelling out the alphas, we get that they're equal. So it's injective. So distinct elements have distinct images. And also, for it to be a bijection, we need that all elements have pre-images. How is this noted? I'm not sure. But basically any G there is X in G such that alpha times X equals G. This is true, and so it's a bijection. So this is indeed an automorphism, and actually this is called an inner automorphism.
Sorry, Ren, I think this one is translation.
Oh, translation. Oh yeah, right.
Yeah, the inner automorphism.
Right, thank you.
For sure.
Translation. This is translation by alpha. Another type of automorphism is the inner automorphism. We fix the same alpha, and then this time we send G to this. So we conjugate G by alpha. And we can also check that this is a bit less straightforward to check. So if, for example, if you have alpha GH alpha, we want to show that this is equal to alpha G alpha minus 1 times alpha H alpha in order to satisfy the automorphism check. But this right hand side, by associativity, I can remove the parenthesis and cancel this out to the identity. So this whole thing equals to just, which is equal, and so it's a morphism. As for the it being bijective, we can find the inverse function by sending H to conjugation by alpha minus 1 this is H. Alright, and we can check that. Let's call this F alpha and this F minus alpha. We can check that F alpha composed by F minus alpha is the identity map on G that sends an element to itself. A few properties related to the normal subgroups and center of group. If we have a group and we have a normal subgroup and an automorphism, the inner automorphism precisely, this is, did I say that? This is called an inner automorphism. If we had, well, we can see that this property here is in some way related to the normality and everything, since because of this weird operation. Actually, if we have H a normal, and well, no, actually it doesn't. If we took the center of of the group, and the claim is that the image of Z with an inner automorphism remains in, and it follows because this is a normal subgroup, as we've seen, and so any operation of this form sends it back to Z. Actually, it does hold for any normal subgroup. So more generally, if H is normal, H is normal if and only if, but we can also say that H, this one, is in H. So it means that if this is H and every element gets sent to some other element, the elements of H will be sent to itself, to themselves. Only for inner automorphisms, by the way. This does not in general work for a normal subgroup. This does not work in general for any normal subgroup and automorphism. The subgroups for which this property holds for any automorphisms is called characteristic subgroup, if I'm not wrong, but I don't think that's too relevant for now. Okay, so if there's any questions on morphisms and all of that's been said before, now is the time. Center, right, partition. Otherwise, we can start on the next thing. But
actually, as we're coming up on, or we just finished the hour, I think it'd be good if we took a couple minutes break right now.
okay, yeah, that's a good
stand up
idea.
and stretch, get some water, all that good stuff.
Yep. Let's say 15 minutes or.
Oh, I think we can do with a lot less than that, since you've only got another 50 minutes left.
Yep.
So keep that in mind.
So yeah, let's be back in 5 minutes. Okay, so we're gonna start. I think for the remaining 45 minutes on sets and like partitions and confidence relations. So partly actually the goal of, okay, first of all, what's the partition of a set? Given a set, a partition is in some way a way to classify the elements of this set. So I write this set as a region, but it can be any set. A partition is a subdivision of the set, so it's a kind of a list of subsets. So in this case, this is a subset, this is a subset, and so on, satisfying that no two are overlapping. So if I take, for example, A and B, then they're not overlapping into each other. It means that their intersection is empty. But I also require that the union of all the subsets equal to the set itself. So in formal terms, we say that if S is a set, we take n subsets. Like it could be infinite, but it's clearer to see it in a finite version. We say that S1 Sn is a partition if I take two arbitrary Si and Sj, their intersection is empty, so it means they do not overlap in the picture. And the union, so S1 union S2 is equal to the whole set. So it's in some way a perfect classification of the set, a perfect no idea what's the right word is, but it's better to show it in counterexamples sometimes. For example, if I take this set, I'm gonna do the following subdivision. First subset shaded in green, and second in blue. So this does not work. Well, this is not a partition because they are overlapping. This is the overlap area, and why that matters is it doesn't make sense to classify something and have the classifications overlapping. For example, if you wanted to say you had 4 objects and you had 2 boxes to keep them in, it would only make sense for you to define not an order, but a way to classify this so that two elements, so that 2 boxes do not contain the same elements. So that's the overlapping thing. You'll have 1 and 2 here and 3 and 4 here, for example, not 1 and 3 and 3 and 4 and 2. That would make sense because 3 is in both. And the other is that it should cover the entirety of the set. So if you pick any random element in the set, there must be a subdivision in which it is contained. So there must be an element of the partition in which it is contained. So okay, this whole subdivision and partition thing gives rise to the idea of equivalence relation on a set. So the goal of this whole section is to define a partition in some way. Let's keep that in mind. Is to find a way to divide a set in non-overlapping, covering the whole set. But in some cases it's easy to define such a partition. For example, if we took the integers a partition would be something like all the negative and all the positives. by including 0 in the positives. So the two sets do not overlap, but they cover the whole of Z. This is one and this is the other one. So this is a partition. So another definition, equivalence relation on a set. So definition, equivalence is a relation on a set is a relation. So a relation is kind of a function that takes as inputs two objects. So x and y, and that outputs an answer yes or no, kind of. So for example, we can define this as being the same, literally, meaning x is equivalent to y if and only if equals y, or something more useful, if we took again the set of integers, we can do m is equivalent to n if they're the same, if they're both odd or both even. So that's a relation. Now an equivalence relation is a relation, so it's a yes or no function on a set that has to follow the three following properties, such that first of all each element is equivalent to itself. So x is equivalent to itself. Second property, if you have an element that is equivalent to another one, it means that is equivalent to x. So you can, if you say A is similar to B, you can say that you can deduce that B is similar to A. I think there are some, it might not be obvious why does this not hold for any relations in general. I can't really find a counterexample. But the third property is that if you have x equivalent to y and z equivalent to y, then x is equivalent to z. So I think similarity is a good thing to imagine, to get some ideas about what an equivalence relation is. So in some way it's like if all x is similar to itself, if x is similar to y, then y is similar to x. If something is similar to something that is similar to another thing, then they're all similar. Or they belong to the same category, if you want. So a way to construct an equivalence, well, this is an example of an equivalence relation, is we take a set and we have a partition that's already defined on the set. We define the following equivalence: x for all x, y, we define that x is equivalent to y if and only if they're both in the same subdivision. So this, for example, here x and y are equivalent because they're in the same, if belong to the same portion, let's call it portion. So here they're equivalent. These elements z1 and z2 are not equivalent. Any x is equivalent to itself because it belongs in the same portion. If g is equivalent to h, it means they're in the same portion. This. If h is equivalent to another h2, it means h2 is also in the same portion as h, and so it is okay. So it is in the same portion as g, and so this does define an equivalence relation if we subdivide it as beforehand. But we'll see that actually defining an equivalence relation on a set also leads us to a way of subdividing, of dividing the set in a partition. So first we call given S a set and X, we name the equivalence class of X is the set of Y in S such that so given an element, and this is denoted sometimes as this, so it means that if I have an X and I regroup everything similar to it in a big set, it is the it is the equivalence class of X. For example, in the previous example where we define this as in Z as being the same parity, so both odd or even, the equivalence class of an integer is all odd integers if k is odd itself, and all even integers if k is even. And this is an equivalence relation. Then a property of this is that given a set, again, the equivalence classes and an equivalence relation partition the set. What does this mean? That's not obviously the same as what's been mentioned before. Is that this time we do not have a partition in the first place, but we do have a yes or no question. Kind of, we do have an equivalence relation that is defined. Now we're going to try to subdivide this into non-overlapping subsets that cover the whole set. And this theorem, the equivalence classes partition the set in a constructive way. It means that if I were to pick an X in S, regroup all elements that is equivalent to it, so this is its equivalence class, pick another one outside of it that's not equivalent to X, Y, and then regroup all elements that's similar to Y, then do the same for until I run out of elements, I will end up with a partition. And this little visualization is not exactly, but shows kind of why it works, is that, say I took an element Z, I regrouped everything that's similar to Z. When I run out of elements that's similar to it, and I start a new little group, there is no way that I will still have some overlapping, because I already ran out of elements that's similar to Z. So it's indeed a partition. And as for and we also can make sure that all elements are contained in at least one of these subgroups, because if there are some elements left that's not contained in an equivalence relation, I keep going on and I do the little grouping for them, and so on. And so the existence of, or definition of this equivalence class relation gives rise to a partition of the whole set. So let's now see some examples on groups and homomorphism. Say G to H, there is a homomorphism F. This is G. The following is an equivalence relation. X, we're going to define that X is equivalent to Y if and only if they have the same image. And we can check using the three conditions, the equivalence check, that this is indeed a relation between, because f of x is equal. So and then also if f of x is equal to f of y, then f of y equals f of x, and that's because this equality can be reversed by the construction of it. If I have x being similar to y and y being similar to z, it means that I can deduce, and so it does satisfy the three conditions, so it is equivalence relation. But the interesting thing is, we saw that it gives rise to a partition, we said, of the group. So we had a group. Let's say this is our discrete image group. We had that by the previous theorem, the existence of this gives rise to a way to subdivide G. into non-overlapping partition on the set. Now we're gonna see what's the influence of the morphism. If I take two elements in the same area, by how I define the equivalence relation in the beginning, they have the same image through F. It means they get sent to the same element. If I take any point in this area, it will get sent to the same image. If I move to another area, everything will get sent to another, but also like so. And same thing for each of them, and so on. So we kind of see that it gives rise to some sort of bijection, even though if F is not bijective itself, by subdividing G into some neat way, we've found a one-to-one correspondence between the elements of H and the area from which they originated. So this corresponds to this. This area corresponds to the second element of H. This corresponds to this, and this corresponds to this. So it is a bijection. And actually we can call the set of classes, that is the set of areas, we define this as G quotient equivalence relation. Or it's also called the quotient set, not a group. It's not necessarily a group because we cannot have, we're not sure to have a law yet on this set, but this is the set of basically the blue part, the red part, the yellowish thing part, and the other blue. This is a set and it's bijective to H. So this is kind of the whole point of why group people define use equivalence relations. An important example of equivalence relation on a set is we take a group G and a subgroup H. H subgroup of G. We'll define the following G on G, so equivalence relation. X is equivalent to Y if Y minus 1x is in G, is in H. So another way to write this is X equivalent to Y if there is some H such that equals H, and this is X equals YH. So actually this equivalence relation is such that the equivalence class of X the equivalence class of any Y is all the Y times H for H. Can also be written as YH, and this is called a coset. So the previous results applied to this said that the equivalence classes partition the whole set. So what it means is G here can be partitioned as equivalence classes, and the equivalence classes are cosets. So AH, BH, and so on. GH. Something interesting about this is that each equivalence class is defined using the subgroup, so they look all similar in the sense that they have the same order. For example, that there are the same number of elements. If I take AH and BH, the number of elements of this is equal if they're finite. For instance, they have the same cardinality. So in some way these areas are the same size. Not only do they partition the group, but they're also of the same size. And the set of cosets, so the set of equivalence classes for this particular equivalence relation, can also be written as GH. This is a quotient set containing all the G for any G in H. Okay, this given like this might seem a bit bland, kind of, for an abstract group, but something we can do, for example, is to see what it means in additive terms. Let's see Z. And let's take a subgroup of Z, which we've seen is of the form NZ. So for example, let's take even the subgroup of even numbers in the integers, and let's define the equivalence relation such as before. So now this is our H and this is our G. M equivalent to N if and only if. Originally it was the inverse of N, so here it's minus is in 2Z. This can be written as M equals N plus 2Z. And what does this mean? Let's compute some equivalent elements. For example, 5 is equivalent to 7. Yeah, because minus 7 plus 5 is 2, which is 2z, 5, 11. Yeah, because minus 11 plus 5 is, wow, 6, which is in 2z. So it's actually all the elements of same parity. If they're both odd, they're equivalent. If they're even, they're equivalent. And so if we define z to z, it will be the set of equivalence classes of integers. But what are equivalence classes? We've seen that they're the cosets. So they're the cosets. So if I take a random integer, its coset would be m to z. Is this correct? Wait, yeah. It will be, well, or also all integers of same parity. I think the more well, I can't say it's more constructive, but a clear way to understand this is, if I want to check the parity of an integer, I can divide it by 2 and then check if I have a remainder of 1 or 0 after the division. For example, 60 divided by 2 is 30. And I have a remainder of 0. If I do the same for 31, I'll have 15. Oh, divided by 2, and I have a remainder of 1. So 1 is odd, 31. 31 is odd, while 60 is even. And in relation to this whole equivalence class thing, if we rewrite the division as equations, we have 60 equals 2 times 30 plus 0, and 31 equals 15 times 2 plus 1. And this is what determines whether it's odd or even. So if we just rewrite this in arbitrary integers m, we can always, by dividing with 2, we can always write m equals 2 times something plus a remainder, and the remainder is 1 or 0. And what this means is m minus r equals 2q. And oh, this is in 2z. So the thing to take away from this is that any elements, so any m, is equivalent to the remainder which you get from the division by 2. And this remainder varies from 0 or 1. And r is either 0 or 1. And so the equivalence classes for this on the integers, let's write this 2z. are precisely the equivalence class of 1 and 0, or also written as 1 times 0 for integers, and this quotient set is z over 2z. So actually, by taking any n, we can do the same process to define the quotient set z over z quotiented and z, and this is called, I don't know what this is called actually. Don't remember. Yeah. So in some way this is the set of all possible remainders in the division by n, which is, well, the equivalence classes of all possible remainders in the division by n, which is 0, 1, and so on until n minus 1. And in this case, it is possible to define a law on this set of equivalence classes so that it forms a group. So we're gonna say that this is a law plus that associates m and n as equivalence classes to the equivalence class of m plus n. It's not obvious that this is well defined, because for example, say in z over 2z, or is 3 or 4, if we were to take 3 plus 5, that would give us 8. But we defined this as only from 0 to 3. But we do not have 8 in here. So, but actually 8, since 8 is itself equivalent to 4, which is equivalent to 0 because it's already in 4z. This equals 0. And the whole question of whether this is well defined or not means that, does it make sense if I have two integers mn well, if I have ab, where if I divide a by n, I'll have a remainder, well, wrong choice of, okay, if I divide a by k, I'll have a remainder m, and if I divide b by k, I'll have a remainder n. Will a plus b divided by k have a remainder of m plus n. That's what this law being well defined would mean. And it is, because we can rewrite this little system of equations as a plus b equals, so the sum of this plus the sum of these, and so it is indeed equivalent to m plus n. And it in a more general, this is basically, we have defined an addition on the quotient set, and so z with the law plus is a group. We can see in another maybe in the book we've seen defined that it works for any g and h if h is normal. We can define a law on the set of cosets so that it forms a group. But it's not any h will work. That's why we require it to be normal, for example. So we have to find examples of normal subgroups. For example, if we were to find a homomorphism to something, if we did by kernel, we can find a law on this set so that it forms a group. Is a group under some law. But yeah, I couldn't. We've ran out of time today, I suppose. So I think we're gonna see this another time, if at all. If there's any questions on what's been said on this week or last week, they're welcome. Not sure if there's any in the chat.
The chat is currently clear.
Okay.
If there are folks want to stay around and answer questions, then would that be okay with you?
Yeah. I'll be here. I can be here for an hour. To be
okay.
So.
Excellent. So it looks like there's that opportunity if folks want it. But otherwise, this will be a good time to officially let people go. Thank you so much, Rand, for the talk today.
Thank you for, being there.